So let's start. So today we Yifan Chen, who is a postdoc in Denmark, a strong biotech group in the Bohr Institute, and he did his PhD in France, Paris, Sorbonne University, and then go to Beijing Institute of Theoretical Physics for his postdoc. Okay, so I'll start.
So thank you very much for the invitation. So today it's my pleasure to first come here to talk about our recent work on using black hole to look for new particles. So that's why I use the title. This is From-Gravity Frontier Particle Physics. So frontier is a word that typically used in the high energy physics community to describe a new direction to look for particles. For example, the high energy frontier and high intensity frontier. So here we use the word strong gravity, which means it's in the region that you have, for example, black hole neutron stars, where the gravity can strongly enhance the search for these new particles. So as I just mentioned, this one I come from the Niels Bohr Institute, which is led by Yifan. So the outline of my talk contains three parts. The first, I will briefly mention the ultralight bosons and how they connect with black holes through the superradiant mechanism. So I think here many people work on. Then I will mention how to use black holes to be a factory of neutrinos, to produce neutrino and accelerating neutrinos. Then I will mention some work we did with this event horizon telescope that used the high resolution observation for the black hole, this black hole imagery, to look for the existence of superradiant cloud. Okay, so let's start. So since I'm a particle physics, I will probably mention this in more like a particle physics point of perspective. So for ultralight bosons, they are kind of like a new spin integral particles that beyond the standard model of particle physics. So for this ultralight bosons, typically we have the spin 0, spin 1, and spin 2. That's the most common one. And for the spin 0, most famous is this axion or axion-like particle. So for example, this A. So first in the particle physics, we introduce this axiom which try to explain this strong CP problem in the quantum chromodynamics, because in the QCD, we have observed that the neutron electric dipole moment is nearly 0. But we know from the standard model electroweak sectors, there are already some CP violations comes from this Parker oscillation. So if you have this neutron EDM, which is vanishing, this is the kind of fine-tuning the particle physics. So one way is to try to introduce a new degree of freedom. This is so-called axiom that coupled to the gluon sectors. Then you can generate a potential, cosine potential, periodically. And at the minimum of the potential, you can naturally explain why this neutron electric dipole moment is vanished. So that's the historical reason. Then more generically, axiom you can think of it as a kind of pseudo-scalar. By pseudo-scalar means it's a parity of the transformation on the parity transformation. So it's different from the other scalar like the theta. So here the phi, I use phi to describe the theta, which is the parity even scalars that can couple to the standard model. So this kind of axiom, or let's call it as dark photon, this spin 1 ultralight boson, they are also very generic predictions from the theory with extra dimensions. So for example, if you start your theory in 5D, if you start this Einstein gravity in 5D, and you say, okay, since we are living in a 3+1 dimension, we needed to do compactification to the 5th dimension. So if you, for example, you do a circle on the 5th dimension, then your metric will be decomposed into a 4D metric plus the 4D spin 1 gauge bosons. So this is the historical, this is so-called consequent series. Then you can have this additional degree of freedom. And if you start with a 5D gauge boson, you will end up with a 4D spin 1 particle plus 4D axion-like particles. So the gauge symmetry in the 5D will be decomposed into gauge symmetry 4D plus the shift symmetry for these axion-like particles. So I mean, this extra dimension appear very generically, for example, in the string theory. So in the string theory community, they call this the axiom in the string theory for the string axioms, which means that since you have a theory from 10D to 4D, so you have a lot of these axiom-like particle predictions. So that's called axioms. And also for the dark photon, it's called string photobus. Means you have a lot of spin 1 particles in your 4D effective theory. So the string theory also predicted one more thing, is that these kind of their mass or this ultralight boson mass, they will be naturally suppressed, exponentially suppressed by the volume of this internal volume. So this gives you why this boson can be very light, like below 1 electron volt. So since this exponential dependence that makes the search for this ultralight boson in this logarithm windows of the mass. That's the motivation from the fundamental physics theory side. So phenomenologically, these ultralight bosons are very interesting because if you think they are dark matter candidates and their mass is below 1 eV, so that's the meaning of this ultralight means. So since that, and then if you look at their density, local dark matter density, you will find their occupation number will be much higher than 1. Then if you sum up this non-relativistic wave individually, they will emerge to be a coherent wave. And coherent wave means their oscillation amplitude is kind of related to the energy density and the mass of the boson. And their oscillation is like classical oscillation functions. And this oscillation frequency is nearly the mass of the bosons because they are non-relativistic. So the kinetic energy are typically small. So that's how people generally look for the signals. If these kind of ultralight bosons, they couple to our standard model sectors. So the oscillation behavior will translate into some observable in the standard model. Then you can try to capture such a kind of oscillation signals in the detectors. I think that's one of the things. I think that nowadays dominant particle physicists are looking for is this axion-like particle induces this oscillation signal in the detectors. And so since we are looking for using black holes, so I should mention how they connect to black holes. So first is, suppose you have this black hole, over there, and you put these bosons around the black hole. So naturally you will form a bounded state because the black hole can attract, has this gravitational attraction, and then you will form something similar to the Coulomb potential, and then the boson around the black hole will form so-called gravitational atom. So this is in analogous with the hydrogen atom. So you will, for example, if you use this Boyle-Levi coordinate, you can parameterize their wave functions. And since it's bounded state, so they will have also all these discrete quantum numbers similar to the hydrogen atom cases. You will have this NLN numbers, and then you will have this time oscillation part omega, and then we'll have this phi angle dependence, which is the azimuthal angle around the black hole spin axis. And M is this azimuthal number. Then SLM is the distortion of the spherical harmonic because you are in a curved space-time. And this RLM is the radial potential, which describes the wave function along the R-axis. So L and M are the orbital angular momentum and the azimuthal number, which around the black holes. So similar to the hydrogen atom, again, is that they also have this so-called fine structure constant, which is proportional to the product of the black hole mass and the boson side. So this fine structure constant determines how much the attraction from the black hole is. Also, it determines the Bohr radius of this gravitational form. So RG is the gravitational radius, which is proportional to this R mass group. So the weaker the coupling, the more extended the cloud it is. And for black holes, I think the difference is that black holes, the boundary condition is different compared to hydrogen atom because now you have this horizons, and which gives you a non-conventional boundary condition. And this will introduce you an imagery part in the energy frequency. So naively, people will think that this imagery part will give you a decaying mode because the black hole basically attracts everything, right? But in some so-called superradiance, in this community, people now think that if you have a rotating black hole, the rotation of the black hole will make this imagery part to be, instead of decaying, to be a growing mode. And this, I think, comes from the early story, as the first by it's based on the Penrose mechanism, which say that a rotating black hole, in principle, you can extract its rotation energy, and then Zeldovich developed it. I mean, Zeldovich is in another story, he said, if you have a dissipational medium, and then if you put a wave on this dissipational medium, in the frame of the dissipational medium, you will find the wave is losing energy. But from outsider, you will see this medium is driving the wave to make it gain energy. And if you combine the two together, you will find that the horizon of the black hole is a kind of dissipational medium. And once the black hole started rotating and rotated fast enough, this dissipational medium will make everything co-rotate around it. So then you will develop this as a growing mode for certain quantum number. So as you can see here, the quantum number is L equal 1 and L equal 1, which means that this state is correlated with the state of the black holes. So that's the ground state of the superradiant mode that you can amplify through this black hole superradiance. And this amplification happens most strongest, most efficient when the quantum wavelength of the boson is nearly the same order as the black hole horizon size. So this, which means if you have a 10 solar mass black hole, you will try to amplify this 10 minus 12 eV electron volt to this ultralight bosons. So for one black hole, typically you can amplify 1 order of magnitude for this boson mass. So it's a kind of a resonant detectors for the bosons. So that's, I think, mostly people know it. So one thing we found very non-trivial, also especially for the particle physics, is that these superradiant growths can give you the cloud mass at most 10% of the black hole mass. Above that, the back direction to the black hole spin will be so strong that you can no longer keep it, because the black hole basically spins down, no longer fast rotating. So you will no longer grow, and then the gravity perturbation to the space-time also, I think, quite strong. So, and if you translate this 10% of black hole mass into the wave function of the bosons, you will find, so the wave function is previously I could find here, it's just the amplitude of this oscillation. You will find that amplitude is nearly 10 to 16 GeV. So this is kind of, because M Planck is 10 to 18 GeV. So this 10 to 16 is nearly the ground unifaction speed in the particle physics side. This is for scale, and for the vector is 10 to 17 GeV, because vector cloud is more closer to the black hole. And to compare this with the local dark matter density around the Earth, you will find that it's only 2 GeV at this size. So this is a 10 to 15 GeV enhancement, 10 to 15 enhancement factor. So compared to the dark matter, so which means any signal on the Earth you are looking for will be much stronger near the black hole. So that's why we say the black hole are powerful transducer for these ultralight processes. So that, yeah, the talk I will mention was based on these factors. So also this superradiant cloud, they will not assume that the bosons are the majority of dark matter. They can be just exist in the theory, and any quantum fluctuation can be amplified to this macroscopic densities. But they are, since they are locally to the black hole, they are just around the black hole. The black hole, we know their total mass in the universe cannot be more than dark matter. So their density can be much subdominant compared to the dark matter density. In the whole universe. Okay, so then let me first mention some like how gravity people mostly do for the superradiant cloud is that in the gravity community, people always introduce a boson with negligible interaction, only the minimal coupling with the gravity. This is, I think, the minimal extension of the GR. Then in this case, as I said, it will grow to this 10% of black hole mass, and then the back direction is so strong that then you stop growing, and the only thing left is the emission of the gravitational wave. So, and the green line shows you how we decay. I mean, it's a loose treatment plot, not very precise, but and the green one shows the GW emissions towards the infinity. So for a stellar mass black hole, this superradiant time is still quite short. So, and if you see some black hole, it's very likely to be in the region back here, which you already extract most spin energy from the black hole. So which means if you find a black hole with a high spin, it can naturally exclude the mass window in a certain superradiant range, assumed by reasonable this black hole this time evolution constitutes. So I think that's many people look for is that they do the plot of the black hole mass and the spin, and if you find some, if superradiancy for ultralight boson happens, then this you will have to find a cut in this distribution. So another way to look, I mean, this is more indirect, and more direct is that, okay, so let's wait for superradiance to happen, and then here you will find a very strong GW emissions coming from the cloud, which is when the cloud is near 10% of black mass. And the cloud can also give you some transition among different gravitational states. So For example, LIGO bubble do, I think Richard is very familiar, is that you wait for a black hole merger and you look at that direction to after this superradiant time scale, you to see whether there's some afterglow signatures of the GW, which is almost the coherent signatures after this superradiant time scale. Wait, if you didn't see it, okay, you can also constrain this the existence of the ultralight bosons with only the mass, because you don't have any other copies. However, from the particle physics side, if you assume this new boson which doesn't interact with itself or doesn't interact with the standard model, it's a kind of like unnatural, because you basically introduce something, it's an independent sector that didn't couple with anything else. So you cannot solve like a strong CP or so once you introduce, for example, self-interaction or the interaction with the other matters, in principle, you will trigger some energy leakage from the cloud. So the cloud will, and this leakage can potentially balance the energy gap from the superradiant, from the black holes. So you are likely to enter a region that the black hole superradiant, which now is a linearly dependent in time, and then the energy flux towards infinity, they will balance each other. So this orange is the energy flux, which depending on what kind of interaction you introduce. So then this red line will enter this region that below this 10% of black holes. So in principle, you will no longer extract the order spin from the black hole, because you no longer exponential growth at this point. So if you find a black hole with faster rotating, in principle, it's consistent with this red region. If the red region is below 10% of black holes, which means the black hole spin measurement can no longer constrain such a scenario. Also, since the red region can be quite low compared to the black hole mass, the GW emission will be quite not very sufficient. Then the GW emission here is also difficult to measure. But the good thing is that you will have this orange energy fluxes, and you will have the cloud in this saturated region, and you will have a very well defined this cloud wave function. So then you can test any interaction between ultralight boson and any other particles. So let me give some examples. Previously, people did, I think, for example, Richard and the Enrico here. So one is that if you introduce the self-interaction between axons, which is very natural, because axons basically have a cosine potential. And that cosine potential, if you extend it to the Taylor explanation, the leading order is a masculine, while the subleading order is a phi-4 interaction. So the phi-4 interaction for axon, I think that always exists, and it's related to its decay constant. So decay constant is how you parameterize the slide. So E will be the MA squared, FA squared, then cosine A over FA. So that's the so-called decay constant. And then the lambda is the MA squared, FA squared. So lambda A4. And if you introduce that, the cloud will start growing, and then once the field value is nearly the decay constant, which means that if you do the Taylor explanation, which means the high order term from here is not negligible, then the self-interaction will make the ground state superradiant state to transit into a higher mode. So you will find the two-state coexist. So you will find the black hole, and you will find this ground mode, and then you have another mode that exists. And the two modes will have some annihilation into each other, and they will emit the axial wave towards the infinity. That emission of the axial wave will balance the black hole superradiant. So that's the saturated phase. And another example is that if you have axial and coupled to the photon, then naturally, this is also very natural, because the axial can typically mix with the pioneer in the standard model. Then this coupling will make the axial decay into two photons. And this decay is kind of not a perturbative decay, but you will have this strong boson enhancement, because the photon field around the black hole, they will accumulate before they escape towards the infinity. And this occupation will enhance this decay by this boson enhancement. So finally, you will find is this cloud with as a photon shield in the larger regions, and this larger region will make the decay to more efficient, which balance this production from the energy gap from the black holes. So the observation channel now is the photon. It's also very monochromatic photon because the decay photon is basically half of the actual mass. It's a two-body decay. So the story of what we learned is that since you can have a very strong field value, so this is in the strong field frontier, then you will have this, you expect the matter production that you couple to any other matter to be much more efficient than the perturbative. So this is typically happened in the early universe cosmology. So in the universe, in the cosmology, we know there's a stage called inflation, and then we know there's a stage called the standard Big Bang universe, which starts with radiation dominated. But in the middle between these two stages, you will have this preheating that the interaction will coherently oscillating in the minimum of its potential and then relax its vector energy towards the matter field that couples with. Another example is this strong field QED, which is saying if you have electric field with the electric field more than the mass of the electron square, then the electric field will be parametrically decay, vacuum decay into the electron positron pair. So this is so-called Schwinger effect. So all these kind of non-perturbative effects can be realized outside the black hole because you have such a strong field. Also, another good thing is that if you change the couplings, if you make the coupling to be weaker or strong, like this red show, the saturated field value, the level of this red lines, they will be shifted. So, and this will also translate into the total mass of the cloud. So, which means the at this saturated level, the cloud mass will be just related to what kind of interaction you introduce. So, interaction scale will determine the cloud mass. So, which means then you have this macroscopic this observation for the cloud mass will give you insight on what kind of interaction between this data. So that's how I related the macroscopic to the microscopic interaction. Okay, so this is my introduction. Any questions so far? Okay, so then maybe I will go to some recent work that they use black hole to be a factory for the neutrinos. So we work with collaboration with people. So the idea is very simple. As I mentioned, the two examples. One is between the coupling between axion and the self-interaction to itself and to the photon. They are all coupling to the bosons. So what we can think is also the ultralight boson can also couple to the Fermis, which is very natural. So one example is that you will have this marginal field, which is in the particle physics very popular, is that you can generate the marginal mass for the neutrinos, and then we introduce this coupling between this phi and this nu L is the left-handed neutrino because instead modern neutrino are basically left-handed. Then this coupling in the background of this marginal background, you will change the dispersion relation for the neutrino because now the mass of the neutrino, the effective mass, will contain the bare term mass mu, and the oscillation part of the mass is related to the this coupling G phi nu, and the phi 0 is the wave function amplitude of the marginal field. And this part will coherently oscillating. And since as I mentioned, the amplitude for the superradiant cloud can be so strong, and the beta term of the mass for the neutrino is very weak. It's like 0.1 eV. So we expect this blue part to surpass this black part. So what happened is that now this cloud, this wave function is coherently oscillating, and once it's oscillating to the minimum of the potential, then you will find the effective mass for the neutrino will become 0. And then the dispersion relation, which is omega dot over omega squared for the neutrino, will be much larger than 1. So this is a kind of non-adiabatic condition, which means the wave function of the neutrino evolves very fast, much more non-adiabatic condition. And then the occupation for the neutrino will be suddenly changed once you cross this minimum potentials, and you will form a so-called Fermi sphere, which means below this momentum, the occupation number is odd 1, and outside it is nearly 0 to satisfy this non-occupation. So once you oscillate to the minimum, you produce a neutrino Fermi sphere, and then the neutrino will propagate. So the next time you oscillate back, you will produce another neutrino this sphere. This will happen outside black holes. And based on this story, we can estimate the production rate for the neutrinos outside the black holes and do the integral of the superradiant cloud. So this is, as I mentioned, this is previously studied by the cosmology community. What they study is you have an inflaton oscillate, and this inflaton, once it coupled to the Fermi, it will generate the Fermi non-adiabatic. So which is totally different compared to the perturbative decay. Because in the perturbative decay, the mass of these bosons are typically below the neutrino mass. You can never decay into two neutrinos. It only can happen once you have this high, very dense, this oscillate background. And what we found is that you don't just have the production, you also have this acceleration, and which is easy to solve once you use this word-line equation of motion for the neutrinos. So then here is the formal unit of neutrino, and then you have this in the Kerr geodesy, this is the crystal symbol. And then the non-trivial thing is that due to the cloud is not uniform, because cloud, you see it has a radial dependence and it has this angular dependence. So cloud is at a different region of the cloud. The effective mass for this neutrino will be totally different. And we found that once you consider this non-uniform distribution for the cloud, the effective mass of the special gradient of the effective mass will behave like effective force, which changes the geodesics of the neutrinos. So the neutrino will be actually accelerated by the additional the force. So it's like in the dense region you produce a neutrino, and this dense region will accelerate the neutrino into the less dense region, and you will gain energy from it. And we can calculate from this superradiant cloud. And this effective mass contains two parts. One is that you will have a radial part, which is radial acceleration. So this green and the orange are two examples that we do simulation at different regions produced outside of inside the cloud. Is that if you produce neutrino very far away from in the outer region, you will directly accelerate towards infinity. And if you produce neutrino very close to this black hole, it will curve around the spin axis. It's like forming a jet of neutrino, and then it's stable towards infinity. So then you will have this angular dependence for the flux produced. So in this story, you need both the spatial and the temporal variation for the wave function of the cloud, then which is necessary for the acceleration to happen. And we can now think whether we can detect such fluxes from a black hole. So, but the story is quite non-trivial because once the neutrino effective mass becomes so small, it can also decay to charge the leptons and the pions in the same model. So what we expected finally is the neutrino and the electron position flux that appear at the GeV. It cannot be higher because higher you will decay in this too. And the electron positions, they will be not easy to detect because the magnetic field will deflect these electron positions, will make them to go to other directions, not from the single black hole. Also, you can consider, here we consider the scalar case. You can also consider that ultralight boson is a vector cloud. So from the vector cloud, you can do this string pair production once this vector is coupled to the neutrino. So you will produce this neutrino pair from this cloud. And then we calculated the fluxes from this vector cloud. We found that their fluxes can be easily surpass this atmospheric neutrino background, which is isotropic.
Sorry, which type of neutrino? Sorry, which type of neutrino?
We assume they are universal coupling. So in principle, you can also do flavor dependent coupling. But I mean, the black hole are typically very long distance compared to us. So even you produce them flavor dependent, they will oscillate and give you quite a universal particles. Yeah. So yeah, it's typically after T that ice cube or other high energy neutrino observation cannot force it. Another is that we consider neutrino because they are in the standard model and they are popular and you can detect them. But in principle, you can make the boson to couple to other hidden sector things. Then you will expect some so-called booster dark matter. It's a kind of dark matter, but their velocity are much higher than the standard dark matter halo, the 10 to minus 3 speed of light. So that's sort of boost dark matter. That's also dark matter direct detection. They can look for such kind of signatures from a given direction of black hole. So that's why we propose this multi-method observation that gravitational wave and electromagnetic signature can look for a faster rotating black hole. You can in principle determine the inclination angle and the spin of the black hole. Then with this information, we can use the neutrino detector and the cosmic ray and the dark matter detector to look for the signature from that given direction, from that faster rotating black hole. So it's you can see that I put some example like a LIGO, this is the DHT, and these are the neutrino detectors, including S2, and these three are the next generation one. Also, the M is a dark matter direct detection, including 10x and 0. So yeah, that's what we try to collaborate with the experimental people for this scenario. Okay, so any questions? Okay, then I'll probably go to the work using the Event Horizon Telescope to look for the ultralight bosons. So for me, the Event Horizon also is next generation. So this week we also have a paper to summarize what the EHT can do with the vector and each other. So so for me, EHT is kind of telescope that has the best spatial resolution so far. This is based on so-called very long baseline interferometry technology. That if you have one telescope, the resolution is bounded by the so-called lambda over d. Lambda is the wavelength of photon, y d is the size of the telescope. So the larger the size, the better the resolution. But if you use this B of BI, in principle, if you have two telescopes, and the distance among the two telescopes can be the effective separation for the resolution. So it's like the D in the so if you have two telescopes on different sides of the Earth, then you will form a telescope as large as the Earth radius. So based on this spatial resolution, so which means you can see it's like €1 coin on the moon, so that resolution. You can see the supermassive black hole too nearby one to this horizon skills. So that you can see the shadow among that and this ring structure outside. So the ring structure for me is very interesting because the ring structure comes from the fact that can come from the fact that the geodesics around the black hole they can form this bounded state of the geodesics. So which means the photon can propagate around the black hole multiple times before go to the infinite. So here different colors means different times that the geodesic can propagate from the observer. So yeah, so this is very precise because this bounded state of photon shield is very precise prediction from the general relativity. So in principle, you can use it to be kind of astrometric measurement for any other beyond the GR theory or like a new physics that I will talk about. So that's for the GR side. Another is that in this black hole images that produce, they not only produce this intensity, which is shown by this yellow color, also they show some quivers, this linear quivers here. So these are the show you how the linear polarization is the direct orientation of the linear polarization. So for the wavelengths that EHT observe, this linear polarization comes from the synchrotron radiation, and the synchrotron radiation is related to the magnetic field. So this image also tells you actually how the magnetic field in the horizon scale they behave like. So they can tell you a lot of information for the plasmas and for the hydrogen astrophysics and how for example, the jet is formed by extracting the black hole images. But for us, one more important thing is that they release all kinds of these photos in like 27 weeks. So and these are separated by like 7 days. So they are 1 week separation. And these 4 days observation, they show very slight difference among each other. So as I mentioned, the cloud wave function is coherently oscillating. If you found 4 images that with very slight differences, in principle, you can couple to a new interaction that changes the linear polarization. Okay, so one more I want to talk is the work in collaboration with Xiao and each other here. So they talk is that we use this photon wave, this bounded state photon object to do this precise measurement to see whether you have this superradiant cloud exists. So, and the mechanism is very simple. So, as I mentioned, this superradiant cloud can in principle emit a gravitational wave, and these are this metric perturbation in the infinite. But locally, just outside the Earth space-time, this metric, the metric perturbation generated by the cloud they exist, and I use this epsilon to parameterize how small they are. They in principle can already change the geodesics of the photons. So the geodesics of the photon will be has this cross geodesics original part plus this perturbation part. And that perturbation is time oscillating, time dependent with the typical oscillation frequency. So here we consider two examples, two kinds of example. One is the scalar cloud, the ground state superradiant cloud, which has these bipolar structures. Another is a vector or tensor cloud. So difference between these two are the scalar, they are carries no speed. So the ground state of the superradiant is they have the orbital angular momentum. So they are correlated with black hole. But for the vector and tensor, they are intrinsically speed. So the ground state for the superradiant state, they are macroscopically polarized. So it's its intrinsic polarization is correlated. So they are more closer to the vectors. And we calculated the effect from these two, and we found it. So for the scalar cloud, the main effect is that you will have this Newtonian potential oscillation, and this oscillation will make the arrival time for the photon to have a delay, and that delay is time oscillating, sometimes advanced and sometimes delayed. But for the vector or tensor clouds, they are this macroscopic polarized wave function. They will also, in addition to this time delay, they will also try to make the photon have some deflections. So here I show one example from one observer to the black hole, and this gray region is the equatorial plane of the black holes, and the white line is the original geodesics, and then you will find the geodesics were divided into different parts in the different oscillation phases. So I used 8 colors to show how the geodesics will be changed. And we try to study in more detail what's the reason of this geodesic deflection. So what we do is do this backward retracing from the observer and go to the black holes. And once the geodesics is more closer to approaching this black hole, you will find you will start developing this oscillation deviation. So these are the deviation for the geodesics for this 4 component in the Cartesian coordinate. So this deviation will start the oscillation, and this oscillation follows the frequency for the cloud. So here the vector and tensor show different frequency because the tensor will immediately couple to the stress tensor for the electromagnetic. Why the vector you need to be the quadratic to generate the measured perturbation first, then couple to the electromagnetic forces. So they initially oscillate, and then once you go to enter the photon orbit, once you start propagating around black hole, the small deviation will start exponentially growing. So here the y-axis are different scale. So this is 0 and 1. Here is 0 and 80. And I mean, this green line is the time that you approach the equator plane. So in this region, the geodesics deviation started exponential growth. And the reason is because the photon ring is a quite unstable structure. So any small deviation, you will start do this exponential growth because it's due to based on the Yifan factor, which is kind of a critical parameter to describe the black holes. And so this part is basically independent of the weather cloud system. So this is the universal consequence for the black hole orbit. So the lesson we learned is that this photon ring orbit can be amplified for this astrometric signatures. So any small deviation, once you go again around the black hole one more time, will be exponential amplified. So it's an amplification of the signature that we want to study. So the observation we proposed is that you to use this photon ring autocorrelation. So this is based on the current technology. With the current technology, you can really see the photon are lensed or not. So, for example, let's go back to the previous pictures. Yeah. So the current resolution are not so clear to see the photon from this light ring because the light ring is the white is around like 0.1 RG. While the current spatial resolution is only 2 RG. So in order to see it directly, to see this photon structure directly, you need to launch your EHT into the space or into the moon. Then you form a baseline as large as the Earth to the moon size. So then you can see directly. But another way, using the current technology, using this 1 RG or 2 RG spatial resolution is based on this the time variability of the emission source. For example, you have this orange point is the emission source. So the emission point will have some time variability since this disk is quite covered. So you have like 20% of the variability for the emissions. And then this point will launch geophysics, multiple geophysics. You will have direct emission, and then you have this blue one, which is so-called N-1 photon, which means you propagate to the black hole one more half orbit. And the green one are so-called N-2 photon, which propagate to the black hole like a one orbit more compared to the direct emissions. And these blue and the green ones, the geophysics, they actually contain the same time information compared to the direct emission. But the two different things is that they were first arrival at the observation like delayed by a certain time, delayed by the propagation time, like here, also by here. So they will be have a time delay, and which depending on how many times you propagate more. Another is that in the image plane, this image plane, the length photon are typically around the ring structure, but they will be separated by this verified angle because the black hole will make them to rotate on this image plane. So for example, the blue and the orange one, they are separated by this delta zero, which is another critical parameter for the black holes, which is very sensitive to the spin of the black hole because it's a kind of free dragging effect. So, and then one way to look for the length photon is that you do this autocorrelation for the intensity fluctuation, characterized by this T, this time delay, and this azimuthal angle shift. Verified. And in this 2D domain, you will find that you will have this peak, which the first peak is the direct emission, and then the blue one is the secondary peak and the third peak. So the observation we propose to look for the superradiant cloud is based on that we say, okay, now the secondary peak in principle can also oscillate because the cloud will generate this information time oscillation. And then this blue part will oscillate coherently based on the typical the oscillation frequency that introduced related to the boson length. And the green one will oscillate more because the length photon, the deviation will exponentially grow. So the green one will oscillate much higher, stronger than the blue one. So once you can look for the blue and the green peak in this autocorrelation, you can try to look for whether this superradiant cloud exists. So based on this story, we can plot this cloud mass to be like 10 to minus 3 for the vector and 10 to minus 7 for the tensor cloud. While the current EHT, I think that's just 10% because the resolution is limited by this. And you need other measurement like the star around the supermassive black hole to do cross the measurement to determine the cloud mass. Why this is just you only need EHT. Okay, so yeah. So my final work I want to mention is that to look for the axions and around the supermassive black hole. Once the axion coupled to the electromagnetic field, then the axion will rotate the linear polarization. So this is what I did from my PhD and during my first postdoc and also going on recently with the EHT collaboration. So the idea is that you have this axion photon coupling, which is the G gamma F-tutor. The F-tutor is the tensor of the EM field. And this coupling will change the dispersion relation for the photon propagated in the axion background. So it's kind of topological effect, which means if you start with the linearly polarized photon, this linear polarized photon, once you go to another point, you will have the rotation of this linear polarization orientation, and this rotation is determined by the initial and the final field of the axion field. So that's why we call it the topological effect. And this relation is holds only in the vacuum space-time, also in the flat space-time. And we, since in the black hole, the story is more non-trivial because the photon comes from this length photon that you propagate around the black hole multiple times. Also, you will have the plasma around the black hole, and then you will have this the emission are quite extended along the geophysics. You will have multiple emissions along the geophysics. So we consider all these effects into so-called covariant radiation transfer. This the formula that so this is the problem to show the how it works. It's just you first launch the geophysics to the black hole, and then along the geophysics you do the integral of the emissions and all this plasma effect like the Faraday rotation and Faraday conversion. Then you go to the observer. So and we also model this accretion disk to outside black hole that EHT. So here's an example of this the image. So the yellow one are the intensity from this original this disk, disk. The green one shows you the linear polarization, and you can the length of this green length, they are how strong the linear polarization makes it. You can see the orientation of this linear polarization, they are oscillating for each pixels. And then around the photon ring, you will find that this oscillation carries the phase. So it's a phase of 0 to 2 pi. This is because the wave function of the axial is a kind of cosine, MAT minus phi. So this phi is the azimuthal angle on the dipole, and that comes from the fact that the axial cloud carries the orbital angle of wave. So that will also enter this linear polarization coefficient because different point you will have different phase delay. So in this plot, we show how on each pixel you will have this linear polarization orientation and how that orientation show up for each pixel. Because you don't just have the photon, you will also have outside. I mean, here it's very dark, but you basically can observe the light in the whole pixels. That can give you the tomography of the axial cloud. And then we can use this EHT observation data. So this plot shows the example of the data from EHT. So that April 5th and April 11th for in the 2017. And that's we can translate this dimensionless axiom for the topics with the J gamma times thing because the filter line is always separated. And the black one are the previous constant. So this is for the topping of this C, and the x-axis is the mass of the bosons, and this rendering is determined by the superradiant the window of the C, and which is related to how many spins that you have. So for faster rotating, you will have larger numbers. And for the next year, so this is for the current year. Why this is for the next generation? The next generation year can do much significantly increase the sensitivities. Okay, so maybe let me conclude. So the key point here is that black hole, if they are fast rotating, they will be very powerful transducers for the existence of ultralight boson in a series of modes. So this is based on this black hole superradiance mechanism that can generate a very macroscopically larger size and more dense cloud compared to the traditional dark matter around the black hole. So it's a local effect. And so once you generate such a kind of cloud and you introduce some coupling between the cloud or to the stellar model sectors, then you can do this parametric particle prevention, which is much more efficient compared to the traditional rapid decay. And you can also accelerate these generated particles in the cloud background. So this is the illustrated plot to show you are separated to this high density value and emit this fluxes. Then you can do this multi-message correlations using the gravitational wave and the electromagnetic observation to find some fast rotating black hole. And then you wait for that direction to see whether there's a neutrino or dark matter comes from the direction. Finally, I mentioned this using this event horizon telescope, this high resolution of this spatial resolution to look for the black hole image around the supermassive black hole. So we consider two effects. One is purely gravitational, that the existence of superradiant cloud, they will deflect the photon geodesics. So they will deflect this photon geodesics into different parts. And then, which in principle you can observe using the photon correlation. Another is that if you have this axial and axial coupled to the stellar model photon, you will rotate the linear polarization. So here's an example: the linear polarization orientation will be rotated or coherently oscillate. Okay, thank you very much. So here this summer, so to connect the black hole, the gravity community with the particle physics community. So yeah, I'm looking forward to it.
Okay. Any questions?
I have a question about the saturation phase. So, is it dependent how it happens regarding if you couple to fermion or bosons?
Yes, for sure.
Because with fermions, I would, at least in the early universe, if you have something like resonant and coupled with fermions, at the beginning you stop the growth, but then you saturate your Fermi sphere so the growth can take over again, right?
Yeah. The Fermi sphere just blocks the efficiency to protect the the boson. But it's like the saturation is only for the cloud. So the cloud will enter this phase that you will constantly emit Fermis. The Fermis will always be kicked away. So it's like a constant flux of the Fermis towards the infinity. Yeah. Okay. For Fermis, they are like not so equilibrium. I mean, it's not an equilibrium state for Fermi, but they are locally. You can see the Fermi flux. They are equilibrium.
Okay.
So when during this saturation phase, is the black hole slowing down?
The black hole will slow down, but only linearly dependent time. So which and that is typically much smaller, because you are this red line. As I mentioned, there is a region that is much below the 10% of black hole. And previously you are exponentially suppressed because cloud and exponentially growing. So that extraction is very efficient only at the maximum of this red lines. And now the red line is below this 10%. So they are linearly only extracting, which is negligible, I would say, in a very long time. And so you can also do some equation of the angular momentum from the plasma from equations. So I would say it's negligible compared to the previous.
So the population of higher speed black holes doesn't tell us anything about the.
It can tell us something. It can exclude the region that the red line is very close to this, but below that we cannot exclude.
More questions? No? Okay, then let's send for speakers.
If you enjoyed the video, like and subscribe.